Okay, so am I audible to everyone? And
Yes.
you can see the screen.
Yes.
Okay. So let's start with this, that some of you in the last lecture were actually talking about that can you give us some live examples or the real life example. And from that, we will start and see few things which are related to the first of our module. That is actually, we are going to talk about the fully connected networks. We already have started to see them, but one should have to really understand it well, because that's the first concept and very, very important concept of deep learning. So, so one thing is that, so in the today's session, we are going to talk about single neuron, then multiple neuron, and then, maybe multiple layered neurons. And once we understand how to train such things, what is happening inside, then in the next week, maybe on the coming Saturday, when we have our next class, we are going to have labs or tutorial session in which we are going to implement several of them using the basics of Python and maybe TensorFlow. So for that, we will be using maybe Google Colab, and we have prepared a tutorial sheet in which most of the things are being written, and you will have to understand the concept that I have covered in these two lectures. I mean, this Saturday and Sunday lectures, and then next Saturday, we will be going to implement and see all that stuff. So with this, let's start this today's session, in which we are actually going to see few things. And now let us talk about okay, so with this, yeah, first thing is actually the Uber driver classification. This is, suppose that I'm talking about a problem, and suppose that I have multiple drivers, driver number 1, driver number 2, driver number 3, and in this way we are having 1000 such drivers. Given such 1000 Uber drivers, suppose that I have asked few questions to them, and they are going to be used as the feature vector or the input dimensional vector. If you really understand that in the last day we are talking about some different x1, x2, x3, x4, x5, and x6. So these are the input vectors. It's going to be the single 6-dimensional input vector for any Uber driver. And suppose that these questions are that what is his age, how many years he is in the service, um, number of complaints about him, the amount of trips he has cancelled, maybe his name as well, or one can say also the average customer rating as well. Suppose that if I have all these stuff, 6 values of for every of my Uber driver, and what we are interested in, along with this, we also have a label that is being called as the ground truth for every Uber driver. The ground truth used to say that whether, so we have 3 classes. First class is good, bad, and average. 3 classes. So we wanted to classify all the Uber drivers, these car drivers, depending upon these 6 values into 3 different classes. And what we are interested to somehow given any di vector. Di is actually a 6-dimensional vector, and we wanted to learn a function which is being parameterized over some theta. Is actually a set of parameters that we wanted to learn. And in our case, it is going to be, if you remember, A1, A2, A3, or W1, W2, W3. And once we learn this function which is being parameterized over theta, it will take any di and give us the label of that driver. Label may be class A, or it belongs to class B, or it belongs to class C. So this label is going to be the predicted label, may be correct, may be incorrect. So that is why what is going to be our loss function, the distance between the label I and the label L, label hat, that is a predicted thing. So what is the distance between the actual label, that is our label I, and its the label that we have predicted, that is label I hat. And for such type of things, and for classification, the loss we are going to use is going to be the cross entropy type of loss. At some point of time, we are going to see that. Let us see another type of problem, this Uber driver rating prediction. So the problem is slightly being tweaked. I am given D1, or say again, this function that we wanted to learn f, that is being parameterized over theta, but this time it is not going to take a 6-dimensional input. Instead, it is going to take a 5-dimensional input, that is maybe number of years of service, age, complaint, trip cancellation, name, or whatever. And it has to give us the, yes, want to say anything? Someone want to say? Hello?
No. Yeah,
Mm.
it was by mistake. Yeah, you can carry on.
Okay, that's okay. Yeah. So what I was saying that given this D1, so for all these UV drivers, 5 values, only given 5-dimensional vector, we are trying to somehow come up with the 6th dimension. This is actually being called as a rating prediction. Here you can predict that if these 5 values are this, then what is going to be the average customer rating of such an UV driver, which is having these 5 values being distributed like this. And here our loss function can be the what is the actual rating and what is the our predicted rating. And one such function can here be, this is actually called as the, this is actually called as MSE, that is called as mean squared error. You can see that what is our current, what is the actual thing, what is the actual Q6 value, his rating, what is the rating that we have predicted. You subtract both of them, get the square of that, and do the half of that. Half is actually being done because you can understand that we need to differentiate this loss function. Once we differentiate this loss function, this 2 is anyways being here, so this 2 and 2 they got cancelled. That's the only thing. Otherwise our thing is being quadratic. This actually also being sometimes called as a quadratic loss. This is the second type of problem. So this is actually called as regression. We are regressing, we are trying to get a function which can somehow regress to a function and keep on reducing our loss in such a way so that we started to match the rating of the two-way driver. So first was classification, second is the prediction, that can actually be seen as the regression problem. Let us see another type of problem. This is suppose that given only one attribute of a film. This is actually movie selection problem. I will give you a movie and you will have to tell me that whether you are going to like it or dislike, or it's a good or a bad movie, whatever. So the only one attribute that I'm going to supply, previously I was applying for every customer or for every Uber driver, I was applying 6 values because I have asked 6 questions to each Uber driver, and that was actually a 6-dimensional input or the 6 features that we have extracted. Here for every movie, we are only going to extract only one feature. Suppose that that feature is actually the critics rating, and suppose that that is only x1 that we have, this critics rating. And for every movie we are going to have some critics rating. Suppose that this is our database in which for every movie M1, M2, M3, and maybe 10,000 such IMDb movies that we have. And for all of them, we have their corresponding ratings of the critics. And for all of them, we also know that whether they are good, I mean, they are being good or bad or liked or disliked. Maybe liked, disliked, maybe 2 classes, or it may be good or bad. This is also a type of classification problem in which we wanted to actually come up with given this CR critics rating, only one single variable for every movie. You will have to tell me that whether it's a good movie or a bad movie. So you can understand here also that the corresponding regression problem can also be that suppose that if I also have its IMDb rating. So instead of directly saying that whether it's a good or a bad, I wanted to say that I will give you this one value. You will have to give me its IMDb rating, which essentially say that with what probability, suppose that it is 7.7. So that's why it is actually saying that with 0.77 probability, I am saying that it's a good movie. And with, so here what is going to happen is that right now it's a classification problem in which given any critics rating, you will have to tell me that whether I am going to like this movie or dislike this movie. Instead of that, that is actually classification. Instead of that, if you somehow wanted to know that by what probability this is going to be a good or a bad movie, or you wanted to regress over the current IMDb rating of this movie, the same problem is being converted into this type of Uber rating problem, in which, given this x1, I am not going to predict its final class, but I am going to predict its single value, and that value has to be somehow being very close to its IMDb rating. So that can actually be the seen, can also be seen as a prediction. So we need to learn. So what we are hearing, so here also one more thing that one should have to see, that that this is the data. Suppose that this is whole of my data, all of my image, all of my movies and the corresponding labels for them, and we divide this data into training and testing and a validation set. In the last lecture we have actually talked about that. And over training, we will train, and what you wanted to know, because it's only one dimensional thing, if you remember, here it's only one dimensional thing, so you need to learn a w1 and w0, only two things, such that for all for all good movies, you just see for all good movies, suppose that for all good movies, suppose that they are belonging, they are being represented by a j superscript. So w1 x1 should have to be w1 x1j. That's actually not the power of j, that is actually just to represent that this feature is actually coming from the good movie. So w1 xi is greater than w0 for all good movies, and for all bad movies, w1 x1 is greater than, I'm sorry, it has to be less than, this has to be less than w0. So for good movies, they, so which essentially mean that you need to learn these w1 comma w0s in such a way so that for all the good movies this inequality holds, for all the bad movies this inequality holds, and which essentially mean that you need to learn a type of hyperplane. Here it's actually a single dimension, so you are only going to learn w1 w0. If it is two dimensional, you need to learn w1 w2 and w0. That's going to be a line, which is actually being shown here in our last recap. Just in last lecture, what we have seen was that we are having our feature space in which we are having x1 and x2, two features. Suppose that we have only two features. In the case of critics or that movie example, we are having only one such feature, x1. Right now, if I say that if I have two such features, all of these movies may be seen like this, which are good movies. These movies can actually be seen as the bad movies, and in between you are going to say that probably I am having, three lines, and too many other lines you can have, which are going to divide this feature space that you can see. This is our feature space that can divide these good and bad movies. But if I see the same thing in the parametric space, you need to learn here two parameters, w1 and w2. Here each and every point which is here can actually be seen as a line over here. Each point here is actually a line, and for each and every point which is here, if you take that line and see that line over here, what is the amount of loss? So loss is going to be how much amount of misclassification and the type of misclassification that you are going to have. So this essentially means that for each point here, you will be having some loss associated to each and every line. And what one should have to do is that every line is actually being parameterized in this parametric space of two dimensions by w1 and w2. We need to explore this parametric space. If I say that this is our parametric space in which we are having, this is our parametric space in which we are having all the possible lines which are being here. We need to explore it in such a way so that at any, you get a point, say w1 w2 here, which is going to really the point for which our loss is actually very less, or one can say that's the minimum, which essentially mean that we are interested to somehow find lines like this. We are not interested to find something like this or something like this. They are not good lines for us, but they essentially are single points over here. So out of all possible lines in the space of w1 and w2, we try to somehow get a solution which is some w1 w2, some point there with respect to which the line that we have it's going to have the minimum amount of error. But how to get such line is that by checking each point of our parametric space. There are infinite amount of lines which are being there, so infinite amount of points which are there in our parametric space. We cannot check this for each and every point, that for this point, for this w1 w2, what is the error, for the other point, what is the w1 and w2, and what is the corresponding error. So if you do that, then it's going to take infinite amount of points you need to check, and hence we actually have said that we require something which is called as the gradient descent type of algorithm, which will be used as our optimizer algorithm. This is an optimizer, our guiding algorithm, that will always ensure that whatever you do, it is going to reduce the loss and let you converge to the minimum loss, whatever the possible minimum loss. Now let us assume the same thing for our critic rating problem, in which we are having only one dimension, that is the critic rating. We wanted to know that given this critic rating, whether my movie is going to be hit or flop, good or bad, like or dislike. So just you see that this is my critic rating, and suppose that this is the dimension for this, that's my x1 dimension. For each and every for each and every this corresponding this x1, suppose that if I have the corresponding which is actually being written there, that's actually w1 and w0. So these are the two things, but we are mostly interested in w1. W0 is just the threshold. So in that, for every threshold, or because critic rating is only single value, you just have to come up with, say, if critic rating is more than this, then it's a good rating, or if it is less than this, then it's a bad rating. So if you say that critic rating is 0.5, 0.5, maybe critic rating is between, say, 0 to 5. If you say that if it is 2.5, that is a safe assumption. If you say everything is good, which essentially mean that if it is more than 0, you will say good, then the loss will be high. If you say only 5, then also the loss is high. You actually wanted to come up with some type of, this is actually the loss function, error function, over which you are trying to somehow move. And in the last lecture we have also seen that as in the last lecture we have also seen that that delta w1, or the change that you wanted to do with respect to your w1 is going to be proportional to minus neta del l by del wi, which essentially mean that how much my loss will vary if I slightly change my w1. So if whatever be the previous w value, this is actually w1, given any given such w1 which is an old value, you have to update it. How you are going to update? You find out its derivative with respect to the loss, loss differentiated with respect to this set of parameters, multiplied by neta and minus of that. So you will get something new, and you keep on doing until and unless your loss is decreasing. Your loss is definitely going to decrease because you are following the gradient descent, which is being proved and being shown that if you update your loss using this type of function, then definitely your loss is going to be reduced. This was the recap. With this, we are going to see some more things. I want to know that if you have any questions.
Yeah, I have a question. So in this example that you gave, how does activation function tie into it?
Yes. So in this, if I say that activation is actually going to come over uh, here, where I have written. So here I have not written. So in this, suppose that in the critic case, sorry, in this critic case, what will happen? Let us see it more clearly. Maybe. So anyways, that is also in my next slide, because this critic thing I'm anyways going to do. So activation is going to come there as well. So in next 2 slides, you are going to see this activation function. Is this okay?
Yeah, that's okay. Thank you.
Okay. So let us go and see which one. Problems of single neuron training. Yeah. So let us go and talk about this thing. Um, yes. So let us see, and soon, as you have said, we are going to talk about this. This is suppose that my critic rating. In the last lecture we have seen that suppose that this is my critic ratings that we have, that is going to be my x1 one-dimensional input. We need to learn this w1 such that w1 and w0 are being used. How you are going to say that w1 x1 more than equal to w0, then you are saying that y is equal to class 1, or is it hit, or it's going to say if it is less than that, then it's going to say that's actually flop, or maybe like or dislike or good or bad. So this is the neuronal setup, in which suppose that some initial values, as I have already said, that the initial values are going to be something that we need to provide. So here the initial values are, suppose that this and this, these are going to be my initial values, and this is the input, this is the bias of my neuron, and this is the output of my neuron. Is this okay to everyone? Is this setting is okay to everyone? Yes. Can you ask it again?
Yeah. So the bias here is basically just the error for the neuron, right?
Yeah, so it's not the error. Error is something else. Bias is actually that see, bias means that it's actually a type of threshold which is being deciding that when this neuron is going to say yes or it is going to say no, which essentially mean that this neuron here, in the last lecture what we have said, it was actually doing is that that it's going to say that w1 x1 whether it is more than w0. If it is the case, then y is equal to 0 or 1, whatever depends upon you. So right now I'm saying that it is saying that y is equal to class A, and if it is less than this, else, then which essentially mean that y is equal to class B. So bias is actually being saying that at when this neuron is going to fire, or means to say that this is class A, else if it is not firing, if value is less than that, then it is saying that it's class B. So that is the bias of the neuron, and that's also being learned.
Okay, thank you.
Okay, if this setting is okay, then that's also being written. So problem here is, so if in the last lecture we have also seen that our problem was that what we have done is that our x1 is our critic rating, and here it is that with a very simple such thing, without any activation function. We are right now not using any type of activation function. We are just taking whatever the things that we have got. What is that? Our output is right now w1 x1 minus w0. That is our output, in fact, because that was equal to that. You can also write it in this way, that our output is w1 x1 plus w0, because bias is anyways going to be learned. It may be positive or negative, no problem for us. The point here is that it is saying that if our value is more than 0.5 here, if our value is more than 0.5, then it is saying that users are going to like this movie, else users are not going to like this movie. That's the point. So if this is the case, then our our deciding function or our bias is too harsh. It's actually like a thresholding type of function. So if it's actually a thresholding type function, which essentially mean that we just have to see that w1 x1, and if your w1 x1 for all good movies, it has to be more than 0.5, and w1 x1 should have to be for all the bad movies, it has to be less than this thing. But you just think about a case which movie is actually 0.49. If it is 0.49 with the critic, we are saying that it's actually a bad movie. And suppose that there is a movie which is actually having value 0.51. This is saying it's actually a good movie. So if it is actually way higher than 0.5, you are very happy to say that it's actually a good movie. But this type of thresholding is every time going to create a problem for this range. When your movie is having a rating of more than 0.4, and less than 0.6. So that's actually a range which is actually an ambiguous range, and at that range this becomes very, very harsh. This function becomes very harsh. Such type of thresholding function, you can see that's also being shown over here. You just need to check here that your summations of this, right now there's only one parameter, that's why it was w1 x1. It may be equal to wixi, and wixi is more than a threshold, and a less than a threshold is the thing that when your neuron is going to say that it's actually going to be activated or not. So that's actually not a very good function. First of all, if this is the function, then it's very difficult to differentiate this type of function, because this is a discrete function. So how one can, somehow use such a function to come up with to solve real world problems. So that is why we started to use this function. So now we started to see this in the form of our activation function. So our z was this. That was previously our z was actually the output. You can say that previously our z was the output, and that was a linear activation. That was actually a linear activation. But now I am saying that instead of my linear activation, we are somehow interested. So previously your z was actually, your y was equal to z, directly going. Now it's not directly going. It's having, we are having a sigmoid activation function, and you can see over here that our sigmoid was 1 divided by 1 plus e power minus of x. Here our x is equal to, this thing. So that is why you are placing things over here, and now you see that this is our logistic function, or you can say that's our sigmoid activation function. And now instead of y is equal to z, our y is equal to sigmoid of z, which is actually represented like this. So now this activation, now our function that we were trying to see previously, it was something like this. Now it is moving very smoothly and going from here to here. That's the graph of sigmoid function. So now you can understand that your sigmoid function can actually be a smooth function, and it's a derivative differential function as well. But one more thing, that previously you were saying that it's actually good or a bad movie. Right now you are saying that it may be good or a bad, I do not know. I am just telling you a smooth value, that is actually a type of rating, that by which rating that you are actually saying that with what probability you are assuming that it is good. Here it is 0.5, here it is more than that. So if it's in this zone, anything which is in this zone, it's highly probable getting more and more towards the good movies, and rating getting high. Here it's actually the probability is getting low and moving towards a low or a dislike or a poor type of movie. So here you can see that it can actually be seen as a logistic neuron in this. So previously it was actually a threshold logic neuron, which will take this value and just see that whether it is more than a threshold or less than a threshold. Here it is saying that instead of that, it is taking all the inputs that we have, taking all these input, it's taking and converting into something like this. This is the function, and this is between, that's actually a squashing function, which is between 0 and 1. So this is actually nothing but the probability by which you are saying that it's a good movie or a bad movie. So that's a difference between, this was not a differentiable function, and that's the difference between no activation or a linear activation. We have to apply the threshold logic. Here it's actually a differentiable function, and that's actually the sigmoid neuron. So if it's a sigmoid neuron, then there has to be a type of some error which is being related to this, which means that we are having certain points. You can see over here that we have certain points. We have a line, a notion of line, and this line is saying that how many points are not properly able to be, we are not able to properly differentiate between them. So there are few points which are given only one neuron, you may not be able to solve that. So you require more and more neurons, that we have seen in our previous case. So let us redefine this problem formally in the form, and then you will see that what are the typical things which are in between, and someone has to really figure out that to set up this type of problem, what are the things that one should have to be looking for. This is actually the data. So now you can see that for IMDb ratings, we have X1, X2, X3, X4. So I have, so many different types of movies for all the movies and corresponding label. This is why is actually the label, whether it's actually a good movie or a bad movie. So I am having, so it's like this, that I'm having movie number 1, movie number 2, movie number 3, and so on. And for all of them, I'm having the critics rating and I'm having the label related to that. So critic rating is some value and the corresponding IMDb rating is actually being there. So given the critic rating, I wanted to find out that what is going to be its corresponding IMDb rating. So as I have said that our model can be equal to, so y hat is going to be, so we know that what is the, this is actually the y value. And the corresponding y hat is going to be 1 divided by 1 plus e power minus wtx. This is very simple. We just have seen that's actually a case of sigmoid neuron. You need not to see this. There are so many other ways. That's actually the, this is the linear regression, that is the quadratic regression, but this is the logistic regression. With the logistic regression, we are saying that it's actually a sigmoidal neuron. What we need to learn? So we need to learn multiple different set of parameters. W, the number of W, the dimension of W is going to be same as the dimension of your input vector. X, if you have asked only one question, input is going to be X1, then W is also going to be W1. If you have asked 10 questions, then weight vectors, so then you will also have to need to learn 10 such weight vectors for this. Learning algorithm. So you also require a learning algorithm that's actually being set as the optimization algorithm. Optimizer algorithm. We just have said that the optimizer algorithm is the gradient descent algorithm, or there are so many different other types of optimizer algorithm that we probably have to somehow see different available gradient descent or ADA-grad or RMS prop or different types of algorithms. Along with that, you also require a loss function. This loss function is the function, suppose that it's actually going to be mean square error, or it can be cross entropy, or it can be different other types of loss function. Most of the time MSE and cross entropies are being used. So these things, if you have, then you can start your and apply your learning module to learn how to understand and learn a single neuron, and how single neuron can learn or multiple neuron can learn. The same thing is being there. Till now, if you have any question, then again you can ask.
I have one question.
Yes, please ask.
On the previous slide, if you could go back. So for the first y hat, that's the sigmoid loss, sigmoid function, and then on the second equation, it's
yes,
on
so
the slide you just covered.
Yeah, this is the thing that you want to say.
And then the second one was a linearized. No, not that one. It was on the latest slide, the last one you wrote on.
Last one is this. Yeah, here.
Yes. So my question was, so for the first y hat, that's the sigmoid. The second one's linear, and the third one's logistic.
The third one is quadratic.
Okay.
Third one is quadratic. First one is actually logistic because that's a sigmoid neuron. So that is actually the logistic function. Okay, fine. Thank you. So yeah, so these are the things we just have to understand, that to rephrase it to our movie model, that suppose that I have this movie, y is going to be the like or the dislike, and our model is going to be the this type of logistic regression. Parameters that we need to learn is actually W. Gradient descent is a learning algorithm that we are going to follow. Loss is going to be the MSE type of loss that we are going to somehow handle. If we fix these things, then we can somehow see in detail that how all these things are being merged together, and one neuron is going to learn the things that are being required. So let us see it again, that suppose that if I have multiple inputs, then it's going to be like this, multiple dimensional input. Right now my input is only one dimension. If you remember, my bias input was always equal to 1, and B is actually this B is previously being written as W0. Right now we are writing it as B. Sometimes it's being written as B, or the bias of my neuron. W, again, you all understand that W is my weight vector. This is my sigmoid neuron. That's why it's a sigmoid activation function is being there. Y hat is going to be my output, which is equal to my fx, and you can see that this is also equal to this thing. That's the sigmoid activation function. This is the setup. And now what we are going to do is that I am going to give you the critic rating, and you will so sorry, here it's actually slightly different. It actually wanted to say here is that if I give you the IMDb rating, can you give me the critic rating? You can do either way around. So here in this example, they wanted to say that I am going to give you the IMDb rating. IMDb rating, that's also a number, and you will have to give me the critic rating. Critic rating, that's actually the Y for us. So we know that for good amount of data, that for each and every movie, M1 to M1K, thousand or millions or whatever the thing that you have in your IMDb, if I give you the IMDb rating, the corresponding IMDb rating, you have to tell me that what is its critics rating. And for this, I have huge amount of training data, in which for every movie I have the IMDb rating and its corresponding critic rating available for me. I wanted to train a network which is going to give me, if I give it the IMDb rating, depending upon these weights and the biases, depending upon this formula, it's going to give me the Y hat. And I know that what is the actual Y value. I find out its loss by Y minus Y hat square and 1/2. That is our loss function. We just have said that our loss function is going to be something like this type of loss function. So if I do that, let us see, and I'm going to use a very, very simple case. And this very simple case is that I have supposed that only two such points which are available for me. And two such point means that I'm having these two values probably not being very easily visible. But suppose that if I have, uh, two such points, only two such points, which is actually being written. That suppose that we wanted to train, what is going to be my two things? I am having X and I am having Y. What is my X? X is actually my IMDb rating. Y is what? Y is my critics corresponding critic rating. And I am having only two such movies for me, because we wanted to see that what is happening inside. So if I have only two movies, movie number one, for which the IMDb rating is 0.5 and the critic rating is 0.2. For movie number two, IMDb rating is this and the critic rating is this. We wanted to learn a function. So what we wanted to do is that we find out our error for both of these points. That's why I is equal to 1 to n. Here it is going to be equal to 2. Find out this loss. And what we need to learn, we need to learn a function f, which is being parameterized over theta. And what are they? My w and b. Given this f that we are going to learn, we apply it for the for movie number one and see that what is the value, find out its loss, then find out the second movie's loss, add both of them. We wanted to minimize and find out that w comma b, which is minimizing my this loss, that for both of the image, for both of this movie, the loss has to be as less as possible. Essentially our function whenever got 0.5, this f function we are learning, f function whenever it got 0.5, it has to give me 0.2, because this is my first data point. My second data point is if I give it to f 2.5, it has to give me 0.9. If the setup is clear and okay to everyone, you want to ask anything?
It sounds good.
Okay. Then let us go and see in slightly think that what we want. We want is actually something which is W asterisk B asterisk, that is the minimum or the best possible parameter that we are looking for. And how to get that, that is the thing that we are going to see when we are having only two such points. Given only two such points, we need to come up with this W and B's which are best for us. So if I say that what is the loss corresponding to any function. So suppose that if I somehow come up with arbit W and B, if I give you some arbit W comma B, This W comma B is nothing but a sigmoid function, because if you see that this is my sigmoid function, and we are trying to learn a sigmoid, we are trying to fit a sigmoid between these 2 points. We wanted to come up with a sigmoid. We change these values W and B. This sigmoid keep on changing. Right now it is this, it may change to this, it may change to this, it may change to this, and at some point of time it may change to this. This is the thing that we are looking for. We are looking for such W comma B, by which if this is my sigmoid that we have learned, then F, whenever I get 0.5, it has to give me 0.2. Whenever if I give this sigmoid F 2.5, it's going to give me 0.9. But I don't know a systematic process by which I can somehow get these things. So what we are going to do is that let us start with some random initialization. My random initialization is suppose that this, which is 0.5 and B equal to 0. If I take B equal to 0 and W is equal to 0.5, put it over here, we have got a function. Given this function, if I find out that if I give this function, suppose that 2.5, what is my output? That is being placed over here. If I give this function 0.5, what is my output? That's being placed over here. This is my loss, number one, loss for my first point, loss for my second point. How well my function is fitting to this, how well my function is fitting to this, and I add both of them. This is the corresponding loss. We want this loss to be as less as possible. So how I wanted to change my W is dependent that if I change my W slightly, what is going to happen to my loss? That is why we wanted to differentiate this L with respect to W. Soon we will see that how we can do that. But suppose that I wanted to do it manually, then different W values and the corresponding B values, you can place randomly, you choose them, and depending upon your knowledge, probably you will see that, oh, if I take W negative, let us see what happened. And then you see that, oh, my loss got increased. So you say that, okay, let us take our W in the positive side and increase it. And maybe our loss got decreased. And then you see that, yes, if I increase my W, my loss is getting decreased. This is a very crude type of hit and trial rule. But if you do that at some point of time, you will get a function which is passing like this. But this is not a very good way, especially it only works when you have very few amount of parameters that you need to play with. You require a way that, so before to see that way, there is a very good example which is actually being shown over here, that this is my W, this is my B, and in that WB space, every point that you have, just see that in that space, if I take any point, this is actually all those sigmoid that we are talking about. You take any point, the corresponding loss is being projected or being plotted in the form of a surface. So you see that here the loss is high, red things are high, blue things are low. So all these things that you can see over here, they are good for us. It's actually low loss, but probably you may start from here, you may start from here, you may start from here. You require someone who will guide you, like it can take you from there to here, it can take you from there to here, it can take you from there to here. It's an iterative algorithm. So do you want, so all of you really understand this error surface, or you want to ask it again? This error surface.
So this error surface is just found by plugging into the formulas on the previous slide, right?
Yes, previous slide, yes.
Okay.
Yes.
Okay,
so you can easily draw this error surface, and over this error surface you will have to explore, maybe starting from this, maybe you are starting from this point or this point or this point, but ultimately you require someone who can take you from there to here, from there to here, from there to this zone. So that is the work of the optimizer that we are going to talk about. Yeah, that's okay. Yeah.
So to find that, one question, sorry.
Yes.
To find that, then you would have to differentiate the loss function to find the optimizer, correct?
Yes, that's correct.
Okay.
So, as you correctly pointed out, that So this is the red is good, not good, blue is good for us. We wanted to come up with the best possible sigmoid which is going to fix over this. All these sigmoids, all of them, actually each and every point over here is actually a sigmoid. All those sigmoids which are maybe somewhat here, all of them are good, but we will have to somehow reach into that zone where we are getting good sigmoids. So what one can do is that, I'm leaving because we just have to see this gradient descent algorithm. So it's actually being proved, and probably I am not going to show that proof because it's slightly mathematically involved, but it's been actually shown that that if you move, so you have got a loss function, you have to differentiate it with respect to your weights, and if you do that and you have to move in that opposite direction, that is what is actually being written, that delta W has to be equal to this. Your delta W has to be equal to this, which is actually the derivative of your loss with respect to the weight. Similarly, for the bias, it has to be differentiated with respect to the bias. So if you wanted to get an update for your weight vector, it's going to be something like this. If you wanted to get your update for your bias vector, it has to be something like this. This is also okay to everyone. This is a simple rule that we have seen in our last lecture as well.
Yeah, sounds good.
Yeah, sounds good. Yeah, so if that is our algorithm, then you start with the first iteration where t is equal to 0. Maximum iteration, you say that I am having 1000 iterations. For all these iterations, what you are going to do, that until your iterations are not being done, you keep on updating, and you just add increment this t. So after 1000 iteration, it's assumed that because it's being proven that if you take gradient descent, move in the opposite direction of the gradient and using a small neta learning rate, then hopefully your loss is continuously decreasing. So after 1000 iterations, whatever be the loss, that you can say that's a lesser loss than the previous loss. So usually it is not being ended like this 1000 after 1000 iterations. It is just that we wanted to see that after 1000 iteration things become small. Otherwise, you see that your loss has to be less than a particular value, because loss is continuously decreasing. So you want that your loss should have to be less than 0.001. So it will keep on doing. It's not being terminated by the condition of the maximum iteration. It will be terminated by the loss. So keep on decreasing that. So if that is the case, then what we are going to do is that formally going to see that how this thing is actually happening, doing each and everything via our hands. It's going to be very simple. Why? Because we are having only 2 points. Our function is also very simple, and a sigmoid very simple activation function, and we are only having one input. So that is why everything is very, very simple. So if you remember, our fx is here is equal to our sigmoid function, which is 1 divided by 1 plus e power wx plus b, and this is our y. You wanted to do this thing, derivative of w, derivative of our loss with respect to w. So that is our differential. So that this is the thing that we wanted to differentiate. Now you see that w is not directly being written or being seen over there, but you can see that this fx is being dependent upon w. So you can now see that actually you wanted to differentiate fx minus y whole square 1 by 2, which is essentially equal to the derivative of this. The derivative of this is actually 2 times fx minus y, and the derivative of this thing, this is not dependent upon w, this is being dependent upon w. This is going to be equal to this value here, because this 2 and 2 got cancelled out, and this is not being dependent. So that's only going to be the derivative of our fx. What was our fx? Our fx was actually this thing we just have seen. Our fx is this. So if you wanted to differentiate this thing, it's directly going to come over here. That's going to be the partial derivative of this thing. I guess that if you're not able to do that, probably that's also okay. You just have to see that the derivative, the good thing about sigmoid function, that suppose that my sigmoid of x, this is my function, its derivative with respect to x is actually equal to sigmoid of x multiplied by 1 minus sigmoid of x. That is the derivative of any sigmoid function. So if you have sigmoid, if you know that the derivative, if you know the value of the sigmoid, you take that and multiply 1 minus that value, that is the derivative for that sigmoid itself. So that is also being written over here, but you are differentiating it with respect to w. So you are going to have things over here which is like wx multiplied by 1 minus f of x. This is the derivative of sigmoid, but here you are having this thing as well, w x plus b. So that's why if you differentiate this, you are going to, and differentiate it with respect to w, that's also going to be multiplied. That is why you are having an additional x term. If you do the same thing for del b, the same thing is going to happen again over there, del by del b 1 by 2 f of x minus y. The same thing. The only thing that's going to change is that everything remains to be the same, but this derivative is also being done, wx plus b. This derivative is being done previously with respect to w, now it's being done with respect to b. So previously you was having an x because wx was being there, here it is now wb, so you are only going to get 1 over here. That is why del w and del b, it's actually this. Here you are having xi, here you are not having xi. Is this fine for everyone?
Yeah, it's good to me.
It's good, fine. So if this is also okay, means that this essentially mean that you are getting derivatives or the updates for w and the updates for b. The updates for w is this, which is having a term of xi. Updates of w or the biases are this, and it's not having any term of xi. Okay. So let us see that what is happening now. The things which are happening now is that probably if you can see, our input is x. So we have two inputs. In fact, you can write it like my x is actually 0 0.5, 2.5, 0.2 and 0.9. So it is saying that this is my one data, this is my second data. First data is 0.5 and 0 0.2. This is the IMDb rating, this is the critic rating, this is the 2.5 and 0.9. By the way, this is the thing that we wanted to do in our, so this is actually single neuron learning. Single neuron learning, that is the thing that we wanted to see. So that is why we probably have to code all that stuff. So here you can see this, that is the derivative. This is actually the sigmoid function and the parameter. You can easily see that this is my sigmoid function. This is my data which is being given in x comma y. Given this, oh, I understand why it's happening, because it's actually the animation we just have to see over here. That is why it's being shown multiple times. That's the final thing. So you have got this x, you have got this y, you have got this derivative. And what was the error? Our error is actually just this value and this. So first it's actually being shown that how we can draw this whole error. This error surface is being shown and this whole error is being shown for us. Now, once we understand that this is our error, you can easily find out this error. We wanted to find out our gradients, and we wanted to find out our gradients with this del of b and del of w. Del of b, you can say fx minus y into fx into 1 minus fx. No x term. Here it is fx minus y, fx 1 minus fx, the same thing, but with x. And what you need to do is that for all of the, how we are doing this gradient descent is that for all the, starting from I is equal to 1, and we keep on showing these points one by one. And once I take all these points, I find out the gradient for this, the gradient for this, and that is my update. You all understand that w is equal to w minus neta. Neta is being our the learning rate. Learning rate is most of the time being fixed as something very small. Here for the toy example, we have placed it as 1, but most of the time this value is very less, different than 1. maybe 10 power minus 3 or 4 or sometimes things like this. So this is our update rule, which is saying that w minus neta times del of w. What is our del of w? This is our del of w, which is actually the gradient of w. What is the gradient of w? Gradient of w is this. How we have got that? We just have shown after derivating the loss with respect to the weight factor. So with this, I hope that you understand that how one neuron can actually be trained. Is this okay? Is this okay?
Yes, this is okay.
Okay. Then, okay. So let us see another very important thing that I wanted to show. That's all the intuition behind different types of neural, this single layered neural network. And now you all understand that we have got one neural network in which we are having one neuron. So you can have one neuron, and you understand that given one such neuron, how you can train such neuron. Then the point is that one neuron is most of the time not suitable, properly able to solve our problem. And that we also have seen, and probably right now I can again use our last example in which I have said that if you have probably only one neuron, then so here we are having two inputs. That's actually two-dimensional input. And if you have maybe only one hidden layer, and in that you have only one neuron, then you may not be able to learn this type of boundary. But if you have two neurons, then first layer can learn boundaries like this, and the second layer can going to learn that the aggregation of these two boundaries, the weighted averaging of these two boundaries, and that can actually be non-linear boundaries. Similarly, if you have more such things, then you can learn something which is completely a complex boundary. That's actually a completely closed boundaries you can learn. If you have probably more layers, then what you can do is that, so with more layers you can have more and more power, and with more layers probably you can learn something which is which is even like going something in and coming out of the boundary. Probably you may learn something like boundaries like this. So if you wanted to learn a boundary like this, if you wanted to learn a boundary which is very, very complex, then you require more and more neurons, and most of the time you require more and more neurons in one layer, and then you require more and more layers. So if you have more and more neurons in layer, and if you have more and more layers, then you are going to get the very nice boundary properties and boundary surfaces that you can learn. So with this, we can really understand that if we have more and more neurons, so maybe we somehow have to train. Given one neuron, how we can train? Given multiple set of neurons, how we can train within one layer? And given multiple layers of such neurons, and in each and every layer, if you have many neurons, then how you can train? So probably these are the things that that are going to be comprising in any fully connected network. So once we understand this fully connected network, so this is actually the fully connected network. If I need to suppose that draw a fully connected network, then we can say that suppose that my input is actually 1, 2, 3, and 4 dimensional input, in which x1, x2, and x3 and x4, this is going to be my 4 dimensional input. And my first layer is suppose that like this, in which I am having 20 neurons. So if I have 20 neurons, and this is connected, my each neuron is connected to every input. So if it is the case, then how many weights are going to be here? Here we are going to have 20 cross 4, that is going to be 80 such weights. And suppose that my last layer, at last I just wanted to say that I am having two classes, class number 1 and class number 2. Only two classes are going to be there. Y1 is going to say that with what probability inputted vector x1 to x4, this single vector that's being input, by what probability you are saying that y1 is equal, y1 is going to be sorry, this x1 to x4, let us say that that is my x that is being inputted. This x is actually a 4-dimensional vector, x1, x2, x3 and x4. If it goes in, what is going to come out? So you are going to get two values. Again, here everything is connected to everything. That is why it is fully connected networks. So here you are going to get 20 cross 2 weights, that's going to be 40. Here you are going to get 80 weights, total 120 weights which are being there in this, that has to be learned. And with this, x goes out, x goes in, which is a 4-dimensional vector, and 2-dimensional vector that we say that as a y comes out, in which y1 is the probability by which we are saying that x belongs to class A, and y2 is the probability by which we are saying that x belongs to class B. So that's our fully connected network. And given such type of fully connected network, suppose that this is my weight vector number, set of weight vectors 1, this is set of weight vectors 2, all the weight vectors 40 things. Suppose that that is my weight vector number 1, and all these 80 things, that is my weight vector number 2. Here you are getting a loss at last. What, how you can update your wi's? That's going to be wi minus the neta times del L by del w1. And then you wanted to know that del L by del w2. Del L by del w2 is going to tell that how you need to update your w2 losses. W2 is going to be, so this thing is not, so weight W2 is not directly related to L. So that is why first del L by del W1 will happen, and then del W1 to del W2 will happen. And that is why this actually a chain rule, because W1 is actually being dependent upon W2, L is being dependent upon W1. So if you want to find out that what will happen if I slightly tweak W2 to my losses, then you will have to see that if I tweak it direct, slight amount of variation here, how it affected this, that is actually this. And then if I change slightly this, how it changes L, that is this. So that is why we multiply both of these things. So that is actually the back propagation that is going to happen. And we will get del W L by del W1, as well as we will also get del L by del W2, and we will get both of these things back propagated. So in this way you can print any fully connected network, and very easily you can write this whole code in TensorFlow, and can somehow, you know, manage to solve this, iteratively solve and get the weight vectors properly. Is this okay to everyone?
What is TensorFlow?
TensorFlow is actually, so here let us understand that what is tensor and why we are saying it is TensorFlow. So TensorFlow is actually a framework which is actually a graph-based algorithm. Graph-based framework. This is actually a, so in usually in C or C, it's actually an imperative language. Java, it's actually an object-oriented language. So this language is actually, TensorFlow is actually a graph-based language. So in which, if in this language, if you wanted to add two numbers A plus B, C is equal to A plus B, then it's directly not going to happen. First you have to make A node, then you will have to make B node, and then you will have to make C node, and then you will say that addition of A and B is actually going to be, addition of this is going to be, you know, something like so addition node is going to add A and B, and you are going to get a C. So instead of doing this thing in one shot, it's actually making a graph. And why this is making a graph is that because you need to find out this back propagation, and when you are doing this back propagation, there is huge amount of derivatives which are going to be there. So that is why this graph-based framework is very suitable to find out this derivative very fast and parallelly. So parallelly you can find out the gradients in this graph-based algorithm. That is why it is TensorFlow. And why this is TensorFlow is that in here A and B, both of them are actually tensors. So vector is there. Tensor is actually the generalization of vector. So A may be a vector, maybe, you know, a one-dimension vector or a two-dimensional matrix or things. So if it is more than 2 dimension, then we used to say that is actually a tensor. So A and B can actually be matrix, tensor, vector, whatever. So that is why we used to say that nodes are being created, and in these nodes we assign certain tensors and they flow in the graph. So that is why it's called as tensor flow. So you find out, you get these tensors and flowing in the graph. That is actually a TensorFlow framework. There's an you know, language, one can say, TensorFlow language.
Sure. Yeah. Thank you.
Okay.
Do we need to learn TensorFlow?
Yes, we need to learn TensorFlow. Yes. For
Okay.
this course, if you wanted to make different things, then so over this TensorFlow. So TensorFlow is actually written in Python, and
Oh,
Python's lower things are, I mean, is they are being implemented in Java, in C. So for best optimization, several things are of Python is actually being optimized in C language, but we will be using Python most of the time from the top end. But when we wanted to do, you know, neural networks, we will have to use TensorFlow. So TensorFlow is using Python. But one more good thing is that along with TensorFlow, there is a wrapper which is being written over this TensorFlow, and that wrapper is actually called as Keras. So Keras is actually a wrapper which will say that for TensorFlow, you will have to do too many things. For Keras, you just have to say that I want a layer. My layer 1 is this. In layer 1, how many neurons are there? I will say my 10 neurons are there. And then you can say that all of them are sigmoid neurons. And then you will say, I want another layer, layer number 2, which is having 100 neurons. And that is also a sigmoid. And then you will say that my loss function is MSE. So things like this. So that is why Keras is very, very easy to use. Yes, it's over TensorFlow.
And TensorFlow, sir, we will be doing lab next week, right?
Yes,
TensorFlow lab.
in the next week, Python and TensorFlow we are going to use to train one neuron. And then we need to train multiple neurons in one layer, and then we need to train multiple layered neural network, multi-layered neural network. So these 3 things we will do, and we will be working on a very simple, specific type of data set. This data set is actually having 70,000 images publicly available. This data set is called as MNIST data set. This data set is actually having handwritten digits, 70,000 such digits. Each image is actually of size 28 by 28, very small size images, and it's being written, say 1, or maybe written 0, maybe written 2, and 28 by 28. All of these images are 28 by 28. 70,000 such images over which we will be doing the classification. And how many total classes are there? Total classes are going to be 10 such classes. First class is 0, then 1, then 2. So given any 28 by 28 image, one should have to understand that how to see an image and say that whether it is the thing which is written, it is 0, or it is 1, or it is 2, or whatever. This is the thing that we need to do.
So before lab, before next week, should we go through some basics of Python, or like what is the prerequisite?
Yes. So see, the way in which we are going to conduct is that we will provide you one sheet in which several things are being written. That what we wanted to do in the upcoming lab. And in the lab, what we are going to do is that we will talk. We will tell you that how Python is being used here, how TensorFlow is being used there, and you just have to use Google Colab type of online platform in which you can implement your things. So we will help you in that, and you just have to, if you are okay with Python, then most of the things are fine.
Also, Aditya,
Yes.
For Keras and TensorFlow,
Yes.
can you give me some live examples, like which sites or which industries currently they have developed or designed in Keras and TensorFlow?
See, I can tell you that if you wanted to see in terms of industries, that everyone is actually using maybe TensorFlow or PyTorch. TensorFlow and
Okay.
PyTorch are the two things. TensorFlow and PyTorch are the two things that these deep learning programmers actually use. Keras is actually for those who really do not want it to do too much amount of coding, and because Keras is just a wrapper, so you cannot do each and everything whatever possible. It's not the full functionality. So for full functionality, we will be using you should have to use TensorFlow and PyTorch.
Okay. So PyTorch is nothing but a the Python package library, right?
Yes, all of the TensorFlow, PyTorch, both of them are actually, so you can say that they are actually the wrappers over Python.
Okay. Okay.
And on TensorFlow and PyTorch, they have written another wrapper, which is Keras. So Keras is very, very simple. I mean, it's not very, very simple, but it's actually easier to manage. And for TensorFlow, you will have to write too many things. And Python, you have to write too many things to make a simple network. Here, as I have said, that if you want a layer, you just have to specify the layers and things, and very straightforward, you can make your model and compile and then run the things. So that is why we will try to use Keras initially.
So for example, if I'm taking one example of like, let's say Netflix or even Amazon Prime videos. So based on the user watching history and watching that whatever he likes that movie, so then it is recommending some of movies. So that is also like one of the algorithm they have used in from TensorFlow or like deep learning.
Yes,
is that
yes.
correct understanding?
Yeah, perfectly correct. So this is that I just have said that you can check my user history and see that what type of movies, what type of ads, what type of documentaries, what I am looking for, and then you learn a model. So suppose that you see that for Aditya Nigam, I watch movie number 1, movie number 2, movie number 3. In this way, in last 5 years, I have watched 50 movies. So if you got this 50 movie data, then you can find out that what are the features. So your feature number 1 is X1, X2, and X3, maybe 3 features. That what is the genre of that movie, who is the hero, Amir Khan or whatever, who is the director, who is the hero, who is the heroine, and all that stuff. So for each and every, if you take these 5, 4, 5, 8 different vectors, so now you see that what you have done, the same problem we have got to understand that this is the movie that is going to like. So in previously I was saying that I am having only one input dimension, and that was critics rating, and depending upon critics rating we were deciding whether it's going to be liked or disliked. Now you are saying that instead of that, my neuron is actually going to see not one value, but it is going to see X1, X2, X3, and X4. And what you need to predict, you need to predict Y. And Y is true or high or 1 for these 50 things, and remaining whatever the things that you have, for all of them, Y is equal to 0. So you train your network, this one single neuron on multiple neurons, or multiple layered neuron, in such a way so that whenever I show you a movie like this or this or this, it has to say yes. Or if I say any movie which is not here, any movie like this or this or this of IMDb that I have not seen, it has to say no. You can learn this, and then you understand that if you show me a new movie, what are those new movies which are actually being here, that probably I am going to somehow say yes for it. Is this okay?
Yes, yes. And I have one more doubt.
Yes.
Yeah, like maybe before going to that. So let's say we have like for the movie example only, we have set 9 X parameters.
Yes.
But in future, like let's say we got one more. Like
Yes.
let's say now we have movie types and movie cast and director. But later again, it is adding the production also. So in our algorithm, do we need to again change our algorithm to add that particular X parameter, or we can write an algorithm like, okay, whatever the new nodes are coming, it need to take that new X parameters and calculate my value?
Yes.
Is that way we can write, or it need to be like, again, we need to have our like a programmer, or they need to go and change again the new parameter and calculate the end result.
Yes. So I will answer it in this way, that the thing that you wanted to say, that is actually called as iterative learning. So this is actually called as I will talk about this, but first of all let me tell you that if this happens, that how we usually do it. And the simple thing is that it is that if you have five features you train your network. This is my network that used to take 5 features. Now after 10 days or 15 days you say that I have got another feature, I have got 6 features. To take the same network, slightly you will have to tweak, not too much, very slightly you will have to tweak, and you will have to retrain this thing. It's not possible right now that from 5 to 6 you wanted to go and you take the same network and convert it into this, because this is actually called as adaptive online learning. So adaptive online learning is right now being an active area in which multiple persons are doing, but that see, you have high-end machines. You just need to change your model and retrain. Maybe in 1 hour or 2 hours or 5 hours you will get your new model being trained for this new 6 parameters. So this is usually happen in this way, that we retrain the network. Online training usually is not being done.
Got it.
Okay.
So this is the methodology called adaptive online learning, right?
Yes, adaptive online learning. So adaptive online learning, as the question that he has asked, is actually very important. And in most of the industries, they wanted to do it in this way. This is not the only thing that you keep on changing your parameters. It may be the case that your training data got increased, that every day I'm watching new movies, every day customers are looking new things, and every day you wanted to somehow learn. So that is also online learning. So for that, it's actually easy because you have got a model and you have got more data of 5 more days. Then you read whatever you have trained, you just have to fine tune your model over this new data. But if you have a new parameter that you have got, to incorporate that you will have to change this network, because previously it was looking for 6 previously it was looking for 5 things. Now it is going to look for the 6 things. So this model is somehow being changed. Then you will have to retrain. But every day probably these deep learning models are being deployed into industries, and maybe every evening, every night, or at some point of time they used to retrain these models for 1 or 5 hours or maybe some amount of time to just see the new data, show this new data to the network and get adopted to today's training data.
Thank you.
So, I have one question.
Yes.
Currently, I'm just trying to understand the difference between the neural networks and general data operations. So when they have the data like this kind of 6 features or 5 features, they know this is a real live production data. So when they run the data operations using business intelligence tools or something, they'll be able to say, oh, more users are watching action movies. And in that, this is the hero more people are watching. So even that way, they know the data, right? I mean, they are able to say more viewers are watching action movies. So the management takes decision. Okay, I think we need to produce more action movie or purchase action movie content data, right? So how is this different from that data operations?
Yes. So whatever you are saying, that's actually the data mining that you are trying to do. So for mining, so there are so many different tools by which you can do different type of data mining. But given, a trend, if you wanted to know that tomorrow which hero is going to be hit, or this movie, whether it is going to be liked by everyone or not, or how many persons are going to like. So this is actually requiring the learning capabilities. So these algorithms that we are going to talk about, they are not trying to mine the statistically most relevant data, but it's trying to somehow understand and learn the structure in which some phenomena or some liking or disliking is going to happen. Once we understand, then we can probably predict the things which are going to happen.
Okay.
Yeah.
One last question.
Yes.
I have, so just for this class and the course in general, and also for next week's lab, do you recommend reading any book or any text so that we can, again, familiarize ourselves or review kind of some of the class materials?
Yes. So what we can do is that maybe tomorrow or maybe in upcoming week, maybe Monday or Tuesday, I will try to share few links from which you can read about Python and TensorFlow. Python, TensorFlow, and Keras. So something related to Keras. So we will be probably using Python and Keras most of the time. So I will give you certain links from where you can brush up the basics of Python and Keras so that you will be able to easily deal with the upcoming lab.
But more so on like texts for machine learning, deep learning, like what we did like mathematically in class today. Do you have any texts based on that?
Textbooks are there. If you are interested, I can tell you. And because if you wanted to see the huge most of this mathematics and other things, then that type of books are also there. Few weeks are there. They just say that Keras code is there. If you wanted to run something, then just have to write this, and it will run. They don't tell that why things are happening. So which type of thing in which you are interested? Mathematical stuff or the only application stuff?
I'm interested in both, like just how to review for this class, like so far what we have done.
Okay. So what we can do is that I'll try to share the stuff as soon as possible. Maybe Monday and Tuesday, I will try to share these things, which is going to be useful for your upcoming lab.
Okay, thank you.
Okay. Is that okay to everyone?
Yeah, I think Aditya sir, you can share with Anjana or Praveen, and we will send them individually.
Yeah, Anjana and Praveen, I will share that. So now what we are going to do is that.
One question. Sorry.
Yes, please.
So in general, like not going too deep into this, like writing or changing. So to do general jobs like into AI or something, how deep do we need to learn those mathematics kind of thing? For example, for an IT guy into deep learning and machine learning jobs. So how deep we need to learn this mathematical kind of things?
See, not too mathematically, I will say, because if you go too mathematically, then that is for academic purpose. And just now I'm going to start a thing, and then you will see that it's mathematically too much involved. But I will only tell you the intuition of most of the thing. So now you understand the intuition behind fully connected networks. So that is sufficient. Now I am sure that once you do the coding, then you will be able to make that Netflix type of example, customer classification type of example, Uber rating regression type of example. You can directly code. If you have data, then you can easily do that. So I guess that just have to really understand the basics and the thing and the intuition behind that concept. And mathematically, all those things are very, very involved. Mathematically, they are too much involved. So all those things are not required probably.
Okay. Thank you.
So we will see that, yes, several mathematically challenging things may be there. We will somehow cut short and try to see that if you wanted to apply, then how you can apply. But I will try to give you some of the intuitions behind such type of, algorithms and model trainings.
Sure. Thank you.
Okay. So the next thing is that we understand that you have got, a decent model, fully connected network. You can say that this is my car, and I know that it's going to be properly moving in whatever the error surfaces over which, because our model is actually a car. This car is not going to be running on smooth surfaces. It's not going to be running on road. It's actually going to be running on that high dimensional error surfaces, and error surfaces are actually there in that high dimensional space of weight vectors. So in that high dimensional space of weight vectors, every weight vector is having a corresponding loss associated to it. In that loss or the error surface, my car of this model is going to somehow roam from one place to another place. You just remember that error surfaces that I have shown. And over that, how you can move. So first thing is that what type of optimization algorithms which are available, which will take you, no matter whatever the initialization that you have got, you just have to know that what is the correct direction in which you need to go. And who is going to tell you the correct direction? Gradient is every time going to tell you the direction. Whenever you are in doubt that out of all possible directions, what is the best direction in which if I go, my loss is going to be decreased, you need to differentiate your loss with respect to your weight, and that is going to give you the correct direction in which you should be moving for. That is the gradient descent algorithm. But that is the one, gradient descent is only one such optimization algorithm. There is something like 5, 7 or 10 different types of optimizers which are available. Out of that, one which is being mostly being used is Adam, and others are also being used multiple times. And that is the thing that in the next remaining time we are going to see different types of optimization algorithm. So before going to start, this is actually going to be very involved, mathematically involved thing, but you need not to see each and everything. I used to cover this when I used to cover this in detail in my classes, but I just wanted to tell you that the motivation behind all possible 5, 6 different types of optimizer algorithm. And in TensorFlow or Keras, you just have to write one word and that optimizer algorithm got activated. So you need not to code anything, you just have to understand the intuition behind them, why they are being used and how they are being useful. So let us see that we have seen this is our data space. This is our data space and this is our parametric space. We all understand this stuff. And if you take this parametric space, and for each and every point over here you are getting the losses, and if you take that and see it in the form of this error surfaces, you may say that my error surface may look like something like this. And suppose that you are maybe here, suppose that, then you need to go here. If you are here, you need to go here. If you are here, you need to go here. If you are here, you need to go here. And this is very easy for us, but most of the time our error surfaces are not going to be very easy, smooth and surfaces like this. That's actually, it's having not any problem which is being, that it's only having one minima over here. So everyone is going, all roads are going to that minima. So that is why you are getting a very easy loss function like this. But most of the time your loss functions are not like this, but they are actually like this. Now you can see that if this is your loss function, then this is having multiple minimas. Multiple minimas are being there. It depends upon what is the initialization. If you start from here, you may got stuck over here. If you start from here, if you may go over here. If you start over here, you may go over there. If you start over here, you may go over there. So there are so many different types of minimas which are actually possible. Out of that, how you can, so here if you can see that, suppose that my error curve surface is this. If you start from here, you got stuck over here. If you got start over here, you got stuck over here, because this gradient descent will let you move down and you reach up to a point, and then you say that my loss got stopped. My loss is not now getting down. Why? Because at this surface you take on going, and at this point of time you are done. But suppose that from this you may go over here, then it's not able to move like this because it got saturated. Gradient descent algorithm got saturated over there. So no more updates are going to happen. Gradient is not going to be changed, because whatever you do, if you go over there, you may say that from here I may go over there. It will say that no, you will have to come over here. Gradient is in this direction. Gradient is in this direction. You need to go over here. And if you are here, then it will say that, oh, gradient is in this direction. You have to go here. So everyone is telling that you need to go here. And what is happening, that your loss is actually after some point of time getting down. So gradient descent algorithm is very much prone to the problem which is actually being called as local minimas. There are going to be too many local minimas, and in this minima it is going to be somehow being fixed, and you will not you will not be able to progress properly. So our objective is that first thing, and that's actually the proof of gradient descent. Again, I'm not going to cover this mathematically involved, but as I have shown previously also, that this only wanted to say is that gradient descent update rule is this. It actually wanted to say that your delta W has to be equal to something which is related to delta del L by del W and eta times of that. So that is the gradient descent update rule, and we just have seen that this is my gradient descent update rule. But we understand that if my gradient descent update rule is this, and suppose that my delta W's are not very high, and the reason is that suppose that you are at a very flat surface. Flat surface means that your delta W's are very small. If your delta W and delta B's are very, very small, you will not be able to move very fast. And that is only because of the reason that every time I'm saying my loss surfaces is something like this. Suppose that your loss surface is like this, then your derivatives are not very big. Your derivatives are very small. Here there is no derivative at all. The height of here, the height of this, everything is same. So there is no derivative at all. So if there is no derivative, WT and WT plus 1, they become equal, and you will not be able to move at all because you got converged, and you are not getting anything to be updated. And that the reason is that my surface something is like this, and here if you are, then it's actually the derivatives not changing is fast, and because of that you got stuck into this region. How you can go here? You require someone who can take you and take bigger steps. How can you take bigger steps? So then it comes that you require something which is actually called as the first variation of our optimizer, which is different than gradient descent, is momentum based gradient descent. You somehow add the momentum. So if you remember, our previous thing was this, that you take that if you take the gradient and just take that gradient and subtract it. Here it's saying that no, not only the gradient, that is actually called as momentum based gradient descent. In momentum based gradient descent, instead of only using the gradients, I also use that what were the steps that I have taken in my previous history. So whenever you move, you just have to ask a guy that what is the direction in which I am going. This guy is my derivative. Now we have seen that what happens if my derivatives becomes very small, and you will not be able to move very fast. So this means to say that suppose that first time I asked the derivative, he said that go in this direction. I move in this direction, and then again ask my derivative, he will say that move in this direction. Now suppose that my gradient, my derivative is continuously asking me to move in this direction. I may probably take bigger steps. How can I take bigger steps? I will be adding. This is actually called as momentum. This momentum of moving in one direction, keep on adding. That is why this is my history, and I add my previous history as well. Keep on updating my history along with my current gradient. So I'm getting my current gradient and keep on adding it to my previous history and update with that previous history, which is having this current gradient also being there. So in this way, you are updating in the direction in which gradient is saying, and you are also saying that if for a good amount of time gradient has said me to move in one particular direction, probably I am going to take bigger steps to move in that direction. So with this, what will happen, that suppose that you are having a surface like this. So here, then your update will be very small, but your momentum is keep on growing, and that is why at this point of time you make it more and more and more and more and more. So you keep on moving fast, momentum keep on adding. So just have to change one word from gradient descent to momentum gradient descent in your algorithm, in your keras. You will get this momentum based update. It's slightly faster. But if you move fast, if moving fast is a good good thing to do. So here you can say that I have got a way by which I can move very fast. So if you can move very fast, then what will happen, that from this you may not be able to stop over here, because from here you will come over here, from here you will come over here, and because you are moving fast at this, you may go over here. You will not be able to stop here, because right now you know how to move fast over these error surfaces. So you do not know how to apply brakes. Brake is only being applied when you iterate over here, and then you will see that what is the gradient direction. Gradient direction is this way. Now you will have to move in this way. Again, you know you are going to be fast, because you are not only moving with your gradient but also with the previous history. So you may be oscillating like this because you know how to move fast. So if you know how to move fast, you may be oscillating. So these oscillations may somehow let your convergence become slightly difficult or slow. From here you may go here, then you may come over here, you may go there, and something like this. That's going to be that you are there, you are multiple time crossing the minima, but you may not be stopped over there because of your momentum. Then it comes that the Nesterov accelerated gradient, this is called as nag. All these things that I'm going to say, they are the tricks that you have to apply if you wanted to train your network properly. The third optimizer is actually the nag. You just have to write NAG, and that got activated in your that can be activated as your optimizer. This optimizer actually says that instead of directly going in the direction where this guy has said, first go there and check that what this guy is saying, and then move into this direction. This is actually called as look before you leap. Let us see this thing as an example. My example is that suppose that you have a suppose that you have a big bullock cart. You wanted to take this bullock cart. It's having driver number 1 and driver number 2. It's having 2 different drivers, and you want to take it into a narrow path. So you just ask a guy, I wanted to go this way. He will say that move in this direction. Before going in, you take this guy D2 to move inside and check that whether it is proper place or not. D2 guy go there, and then it will tell you that yes, we can go. So the same, and then here you ask this guy again that whether I have to go inside this or not. So what is going to happen here is that we will first start from first place, take a step into the direction in which my previous history is saying. History is saying that you will have to move in this direction. Then you move in that direction because historically that was the best possible direction in which one should be moving. Why? Because last 5 times whenever I asked anyone, he said me to move in this direction. So that is why this time also I'm moving in that direction, and then I move slightly in that direction and ask the guy what is the direction. This guy is actually my gradient. So instead of asking gradient over here, I move first using my gradient history, and then I ask my gradient again at that point of time. So that is actually the idea behind Nesterov gradient update, Nesterov accelerated gradient. So this actually becomes even more faster, but this will help you in this way, that suppose that you are at this point, and then in the so your update is in this direction, your gradient is in this direction. So so your update is in this direction, or your gradient is telling you to move in this direction, because gradient is actually in the opposite direction. So gradient is telling that you have to move in my opposite direction. So it is saying that you have to move in this direction. Here also update is in this direction, gradient is in this direction. Here also update is in this direction, gradient is in this direction. And now from here you will may probably, if you only use update, not the update plus gradient, because we are using in momentum, we are using update and gradient, both of these things. So it will take you up to maybe only take the updates, then you may be over here, and then you will ask your gradient, then it will say that you will have to move in this direction. So if you take both of these things, update and gradient, probably from here it may take up to another bigger point, and from that you will be oscillating more. If you do not want to accelerate more, then you first take the update, go into that direction, and then see that what is the gradient in which one should be going. If you take only the updates probably you may be here and then see that, oh, gradient is taking us in this direction. So that is why your turns or the U-turns are not going to be that big. So that was the motivation behind NAD. Then it comes the ADA grade. ADA grade is the adaptive learning rate. Here there is a big and important thing that one should have to understand, that if you wanted to move fast, why don't you directly play with the learning rate? You can increase the learning rate and it will let you move very fast. That is being seen as not a very good idea, because if you directly increase that learning rate, then you will be running very fast. You want it to run fast, but then what will happen, that you will be running very fast, and in this type of scenario will be continuously, will not be able to stop, because it will run fast on the plane surfaces, it will run fast on the elevated surfaces. So if you run very fast on the elevated surfaces, then you will only be oscillating like this. So that is why learning rate is not being directly being, incremented. But let us see a very specific scenario. This is ADA grade and then RMS prop, and then we will talk about ADAM. These are the three more things which are being left. Then we are done with our lecture. So let us see that what is the problem that we used to face several times, and let us understand it in a best possible way. Let us first let me first remind you that when we were seeing this derivative of Wi, it was having the corresponding xi along with it. This xi was also there, which actually meant to say that if you wanted to change any weight vector, the corresponding xi is also going to play some role there. And suppose that your xi is 0, then the weight is also 0. And if xi is high, then the weight is also high, because xi is directly dependent upon, so wi is directly dependent upon xi. Now what is this xi? Xi is actually some input we are talking about. Now there can be multiple different types of inputs that you are going to give your data. Now let us talk about that, my initial Uber example, in which I was trying to say that whether the given driver is a good driver or a bad driver. In that, I was having multiple inputs. One was that how many amount of complaints. Now assume that I'm having one attribute xi or x5, which is saying that is there any criminal case being there or not for this driver. And suppose that value is, most of the time, for most of the driver, it is going to be 0. But for few of them, suppose that it's going to be 1. So what is going to happen is that most of the time this input variable xi or x5, for most of the driver, it is not being set. It is actually 0, but only few of them are having this value equal to 1. Then what will happen, that this parameter or this input variable is actually being called as a sparse variable. If it's actually an sparse variable, for sparse variables you can see that updates are very rare, because everyone is having value as 0. If value is 0, then its value itself is 0, this value itself is 0, then the weight update is also very small. If your weight update is small or actually 0, then other parameters like the age or the how many years he was being there, these values are going to be somehow being, the weights related to them are going to be updated, but the weights related to this sparse parameters, they are not going to be updated very frequently. And if that is the case, you can understand it in this way. Suppose that xi is, are you mentally disabled, are you criminal, having any criminal record, gone to jail. All these parameters, if they are being there, they are not going to be very dense. Only few of the customers, few of the input variables, input vectors are going to have this value being set as 1. Others are going to be very other customers are actually having it as to be 0. So the update for the sparse inputs is going to be very small. So suppose that this is my sparse parameter, sparse input, and this is my dense input. So in the direction of my sparse input, which is this, I will not be able to move at all. And the reason is that you will not be able to move because this is my lowest zone. This is the error where it's actually getting very small, but I will not be able to move in this direction because I am not able to iterate in that direction, because my delta wi, where I is a sparse vector, is actually very small. So I will not be able to move in this direction, but I will be moving here and here and here, and very slow I can move, very slow I can move whenever I can get the update. That is why it becomes very, convergence becomes very slow in such cases. Is there a way by which I can directly go from here? Suppose that I am here. Is there a way I can directly come here, or I should have to go like this? If you go like this, then it's going to take huge amount of time to converge. So this is the main and the big problem that is being solved in ADA-GRAD, adaptive gradients, and this is the formula for this. Anyways, I'm not going to tell that how it is going to say, but that is only being doing to work. I mean, the intuition is that if there is a parameter which is frequently updated, how frequently you are updated, your learning rate is going to be dependent upon that. If you are very frequently updated, your learning rate is less. If you are less frequently updated, your learning rate is high. So now you can see that we add all these WTs. WT is the gradient, and that's got the update. So it is telling that how you are updating, how much you are updating, and historically how much you are updating. And with this VT, I just weight your learning rate. So I'm annealing your learning rate. Your learning rate, no matter whatever it is, if you are getting more and more updates, your learning rate is getting less. If you are getting less learning rate, if you are getting less updates, then your learning rate is not being updated or annihilated that much. So that is the way by which, if you are getting more and more updates, then your learning rate is very fast getting reduced. If you're getting less updates, your learning rate is not that fast reduced. That is the way by which ADA-GRAD actually helps to solve this type of problem. But ADA-GRAD itself actually got into a problem of the following thing, that the dense parameters which are frequently updated, their learning rate is annihilated or reduced very fast. And because they are continuously updating, their rate is also getting down. At some point of time, what will happen, that their learning rate becomes so small that the same problem started to happen to the dense features. Those features are really dense. Every time you do anything, that the weights corresponding to that is actually being changed. The weight got changed, it got updated, and a learning rate got reduced. At some point of time, your learning rate becomes so small that you will not be able to reduce it much, and you will not be able to move in that direction. So you will not be able to make even progress in the features which are actually less less frequently updated. So in RMS prop is the being used in such cases. RMS prop is actually trying to avoid the problem that is going to happen with respect to the ADA-GRAD problem. And what this RMS prop actually does is that that's actually the weighted average. Instead of giving this full weight, it's now being giving the weighted average. Weighted average means to say that I am not annihilating something very aggressively. I'm going to reduce your learning rate, that is fine, but your learning rate is not being annihilated very fast. It is going to be reduced slowly. So previously I will take the annihilation very fast. Right now it is slightly slow. You can easily see this thing, that this function and the previous function, the growth of this function is, the growth of this VT is not as fast as of the ADA-GRAD. So if you take this RMS prop, that is the weighted averaging of the historical vector and the this delta WT, RMS prop is less aggressively reducing the learning rate. So with this, actually RMS props perform slightly better than the ADA-GRAD. The final thing is that this is actually ADAM. I can tell you that for all the things that I have told, I just have told just to let you understand about Adam, because Adam is the one which is being used by everyone. That is the most recent and the best possible optimizer that is being used for any optimization that is being required. So you will not be using stochastic gradient descent, SGD, gradient descent, RMS prop, ADA grad, but you should be using Adam. What is this Adam? It actually says that along with RMS prop, whatever you are doing in RMS prop, that is the weighted averaging over the delta W squares, you also do the momentum thing, because momentum we just have. So RMS prop is only annihilating the learning rates, and learning rates are being annihilated via delta W square values. Here, along with that, if you use the momentum, then along with RMS prop and the momentum, that is the thing that everyone is interested to do. Everyone is interested to do. So this is actually the formulation for this. In 2 minutes I will explain this and then we are done. So this is actually, if you remember, that the MT, that is actually the momentum term. This momentum is saying that how I am going to use my WT along with my previous history. So WT and the previous history, we are weighing them, and this is my second moment. If you remember, delta W is the thing by which we are going to update the thing. Instead of updating with delta W, I have said that update with delta W and add a momentum to this, and then use this empty to somehow manage this thing. So with this empty, we are going to update, and that is the thing that we also update in the case of our momentum. The only thing is that our learning rate is not fixed, and it is being also being governed or being annihilated by our velocity vector, or the velocity that we are saying, that delta WT square. So this is actually trying to tell you that you should not be annihilating your learning rate for very dense features very fast. We just have seen that the intuition behind the RMS prop. So RMS prop says that your learning rate is going to be somehow annihilated. It's going to be somehow reduced, but not that much reduced, because I'm going to do the weighted averaging of my delta WT squares as well. And my update is going to happen with respect to the momentum base. So this is the momentum term. So adding this momentum term over here and using the RMS prop as well to annihilate or change my learning rate depending upon the frequency by which I am, my parameters are being updated. If I do that, then that is actually called as Adam. So this is the actual, so we are done with this. Why this is being working? There are so many things which are being there. Maybe in the next lecture we will talk about slightly more about the practical values about the Adam. But Adam is the best possible optimizer. You just have to write Adam in your optimize as your optimization algorithm. It will run things for you. If you have any question, then you can ask. I guess it's slightly more involved and complex thing that I have covered.
So these mathematics things, like will in day-to-day work normally we may not be using in machine learning, right?
Yes, they are not being used. They are just for the intuition. Whatever the intuition that I have developed, I was trying to say, it is just because of the mathematics which is behind that. So I have given you the intuition. That is the correct intuition. If you wanted to see that why, then these are the equations and the parameters which are being tweaked and trained in this way. So mathematics is most of the time just to support that why this thing is happening.
Just to explain behind the scene what is going on, right?
Yes, behind the scene what is going on.
Okay.
So in Keras, if you just type in, for example, Adam or RMS prop, it'll do all this in the behind the scenes, correct?
Yes, everything is being done behind the scenes. It is just like that. You just have to change few keywords. You have to use few keywords and things are being done for you.
So in that case, what are the limitations of Keras? Like, is it only for the basic neural networks, or can it be applied for anything?
Yes, see, it can be applied to anything. The only problem is that if you wanted to do each and everything, that suppose that you wanted to make a neural network, cut it into two parts and then add another neural network and train it with a different type of loss, with different layers and some other type of optimizer, then everything is not possible in Keras. Then you will have to go for the TensorFlow, and sometimes you will have to go even lesser than that, maybe in some Python coding. But if you wanted to use some standard things, simple things, suppose that you have your own loss function, then Keras creates some problem. Then probably you will have to use TensorFlow.
Okay, thank you.
All the standard stuff which is being required, being done, you can easily do it using Keras. And Keras is also day by day improving. 3 years back, Keras was not that much good. But right now, Keras has huge amount of functionality. And previously, I every time used to say that Keras cannot be used to solve most of the things. But now my students used to say that they can use Keras for several things that were previously not being possible.
Okay. And then one more question. So
yes,
for all these applications packages, we'll have to install them on the computer and then everything for us to use for the lab, right?
see, for Google Colab, so we will be using Google Colab and things will be installed there. So we will talk about that as well. So you need not to install things over your own machine. You can install those things definitely on your own machine. We will tell you that what are the packages which are required. But if you wanted to use your own machine for your programming, so you can use that as well. But on Google Colab, you can instantiate a machine which is having the stuff that is being required. So it is as simple as that in Google Colab.
So basically, this is cloud-based lab where they give you pre-configured, so you don't have to configure anything. We can write the Python code and start running, right, Adit sir?
Yes, correct.
And one question. So you said Atom has been developed. So it's a recent algorithm, or is it something developed 1 decade or 2 decades ago?
See, it is at least 5 or 8, 10 to 10, at least 10 years old. But practically it performs very well. And still after Atom, there is EU. And there are at least more than 20 different algorithms which are being developed. But these Atom is now being a standard. So you can use this optimization is got saturated with this Atom.
Okay. Thank you, Adit sir.
Yeah, that's okay. Anything else anyone wanted to know?
So today's session is over. If anybody has any question, feel free to ask.
Just one last question to substantiate the intuition. Like, so in this lecture, you gave a lot of intuition behind the various algorithms that you can use for optimization. But if we wanted to maybe go over the intuition that you gave us, obviously we can rewatch the lecture, but are there any websites or texts that we can look at such that we'll be ready for actual applying next time? And also by knowing the background well.
Yes, so there is huge amount of text and other things which are available, and I understand that you are interested. So what I will try to do is that I will try to share this stuff with our this NFI guys. So they are going to give you that stuff as well. So I will give you links where they are being available, deep stuff. So whatever the intuition that I have given, the places from where I have got, I will give those things to you. And by the way, there is huge amount of lectures and these things which are available on YouTube. So you just write Nastro or NAG on YouTube, you will get lecture on NAG, full lecture maybe on NAG or maybe on SGD, gradient descent, Atom. So there are so many persons who have explained this stuff. But I will give you a few links from which you can read.
Okay, thank you, sir.
And if you have any doubt, you can always reach out to Adit sir.
Yes. If we have a doubt, how can we reach out? Do you provide email?
Yeah, I think Praveen would have sent you.
You can write down to support@infini.com. And also the stuff which Aditya will be sharing with us, we'll be sending it to your email.
Okay, sounds good. Thank you.
So if
So any more questions?
Yep.
So all the session recordings are also available to all the participants on the dashboard. So they can go through the session recordings again from their dashboards.
Sure. Thank you.
Yeah.
Thank you so much, Aditya sir, for this wonderful session. Hope all guy would have enjoyed.
Yeah.
Okay. Okay.
Thanks
see you.
everyone.
Thank you.
Yep. Bye.
Thank you.
Bye.
Thanks, Aditya. Thank you. Thanks, everyone.